How's it going, everyone? In this video, we are going to discuss the moment of inertia. This is a concept that often people struggle to understand because they're given a formula of what it is. They're explained how to use that formula, but they don't quite understand, well, what exactly is moment of inertia? And that's what we want to explain here. So before discussing moment of inertia, people tend to be familiar with these equations of motion, with kinetic energy being equal to 1/2 of mass times velocity squared, force being equal to mass multiplied by acceleration, and momentum being equal to mass multiplied by velocity. Now, all of these equations have to do with velocity, or the change over time, which is what acceleration is. But what if we're interested not in velocity, but in angular velocity? So specifically in the change of an angle over time. And that means we're describing the position of an object using an angle, in this case theta. So first we have to fully understand what that is. Let's say we have some point mass over here, and it's rotating around some point, which we will call the origin. And let's say it rotates by an angle of theta, and theta is measured in radians, and it maintains a distance of r from the origin. Well, then it covers a certain path, okay? And the length of that path, L, is equal to r multiplied by theta. Now, if we take the time derivative of L, we get velocity, right? The velocity is dl by dt, and if r remains constant, that's going to be equal to r times d theta over dt. Okay, so the time derivative of theta, well, we can define that as omega and call it angular velocity. And so we have our tangential velocity is equal to the radius multiplied by angular velocity. Okay, our tangential velocity is always tangent to where the point mass is as it rotates. Our angular velocity describes how that angle changes with respect to time. Now we can take the time derivative again. Okay, if we take the time derivative of velocity, we know that that is equal to acceleration. Okay, that is dv over dt. And again, if r is constant, that's r times d omega over dt. And we will call that alpha. That is our angular acceleration, right? So we have velocity is r times angular velocity, and we have acceleration as r times angular acceleration. And with these concepts, angular velocity and angular acceleration, we can actually see where moment of inertia comes from. So let's take kinetic energy. 1/2 mv squared. And instead of v, let's put in r omega. So we have 1/2 m times r omega squared, or 1/2 m r squared omega squared. So in this form of the equation, it's still the same kinetic energy. It's just in terms of angular velocity omega. And we see it's multiplied by this mr squared. And compare it to kinetic energy as a function of velocity, and we see that if v squared is replaced with omega squared in how the equation looks, well then m must be replaced with mr squared for the equation to still hold true. So when focusing on angular velocity, mr squared seems to play the same role as m does when we're looking at tangential velocity. So then we ask ourselves, well, what exactly is mass? what role does mass play when we're looking at kinetic energy? Well, if you have a certain amount of energy, okay, and, well, if we rearrange this equation, it will look like this, right? If we have a certain amount of kinetic energy, the square of velocity that we get is inverse proportional to the mass. Okay, what mass is, okay, what inertial mass is, it's an object's ability to resist changing its velocity when a force is applied onto it. Okay, we just look at Newton's equation, F equals ma. Well, if we rearrange this, F over m equals a, again, we see what mass is, right? If a certain force is applied onto an object, the acceleration that happens as a result of that force is inverse proportional to the mass of the object. Okay, the greater the mass, the less acceleration there will be. Okay, or when we're looking at it in terms of kinetic energy, okay, given a certain amount of kinetic energy, the greater the mass, the smaller the velocity of that object is going to be. Okay, so that's the role that mass plays. And what we see when we write kinetic energy in terms of angular velocity is that if we rearrange this, the greater this mr squared term, the smaller your angular velocity is, given the same kinetic energy. So mr squared seems to play an analogous role to mass. Okay, mr squared when we're dealing with angular velocity, and mass when we're dealing with tangential velocity. So let's create a name for it, and let's call it moment of inertia. And this is kind of analogous to mass, okay, except when we're dealing with angular velocity, right? It is an object's ability to resist changing its angular velocity. Now, that's kinetic energy. What happens if we deal with force? Well, force is equal to mass times acceleration. If we replace mass with moment of inertia, which is like an analogy to mass when we're focusing on angular motion, and we replace acceleration with angular acceleration, well, then we get something that actually has different dimensions. Okay, so we can't call it force. We'll call it something else. We call it torque. Now, this might not be how people are typically introduced to torque, but when we break this down into what it's equal to, I is mr squared, and alpha is a over r. Okay, because if you remember up here, if we rearrange this equation for alpha, we get a over r. And then our r's cancel out. So we have torque equals mRa, or r times ma, and ma is force. Rf. And that's typically how people are introduced to torque. Rf. But where does it come from? Well, it's the angular analogy to mass multiplied by the angular acceleration, okay, which you can see parallels F equals ma. But there's another way we can reach the same equation. If we have a situation where all of the force applied onto an object contributes to its kinetic energy, well then the spatial derivative of kinetic energy should equal the force. Okay? And we can see that when we look at tangential velocity. Okay? 1/2 m comes out of the derivation process because it's constant. And then we have 2v dv by dt, dv by dx. And dv by dx we will write as dv by dt, dt by dx. And we notice that 1/2 cancels out the 2. dt by dx is the reciprocal of dx by dt, which is velocity. So we have this canceling out as well, and all we're left with is m times dv by dt. Well, dv by dt is a, right? Acceleration, mass times acceleration is force. Okay, now if we do the same thing with our kinetic energy, but we look at the rate of change with respect to our angular position rather than x, right? We have that 1 over 2 mr squared, that's our moment of inertia, times omega squared. Well, if mr squared are constants, we have d omega squared by d theta, which gives us 1 over 2 mr squared times 2 omega d omega by d theta. And our 2's cancel out, right? 2 over 2. So we have mr squared omega d omega by dt, dt by d theta. dt by d theta is the reciprocal of d theta by dt, which is omega. And when we have these two cancel out, we get mr squared d omega by dt is alpha, which is moment of inertia times angular acceleration, which is the torque, right? So we have two different directions from which we can define torque as being moment of inertia times angular acceleration. We can just say, well, it's the analogy of mass multiplied by the angular acceleration. Or we can just take the spatial derivative of kinetic energy and end up with the same property. Okay, so once again, we see that moment of inertia pop up. All right, so we've covered two of our equations, right? And what's left is momentum. Okay, so momentum is mass times velocity. And the time derivative of momentum is the force, right? M dv by dt, which is ma, right? So if we come up with a concept of angular momentum, well, then the time derivative of that should be the torque. Okay, since torque is our angular, when tracking angular motion, torque plays the role of force, right? How we're used to thinking of force. So, well, if we have torque as being equal to mr squared multiplied by alpha, okay, what would we have to take the time derivative of in order to get torque? Well, we would have to take the time derivative of mr squared multiplied by omega, right? Because dl by dt equals mr squared d omega by dt, which is mr squared alpha, right? And that is equal to I alpha, which is equal to the torque, okay? And just like momentum is conserved if your force is equal to 0, right? Because if your time derivative is equal to 0, it means it's a constant, right? It's conserved. Similarly, if your torque is equal to 0, then angular momentum is conserved because the time derivative of your angular momentum is 0, which means it is conserved. So, just to recap, what we end up with is our kinetic energy is 1 over 2 mv squared, or if we want it in terms of angular velocity, 1 over 2 I omega squared. Our force is equal to mass times acceleration, and our torque, if we want equations describing angular motion, is our moment of inertia multiplied by angular acceleration. Our momentum is mass times velocity, and if we want to focus on angular motion, our angular momentum is our moment of inertia times angular velocity. And again, sometimes people are not introduced to angular velocity in this way. They are introduced to it as a different equation, which we get from here, right? If we replace omega with v over r, which is what it is, right? Then the r's cancel out and we get mrv. And often people are introduced to angular momentum in this manner. So that's what moment of inertia is. Okay? When we rewrite kinetic energy in terms of angular velocity, we get this I, which is equal to mr squared, which seems to play the role of mass when we're looking at how much an object can resist changing its angular velocity. And when we multiply that by alpha, angular acceleration, we get torque, which looks like the equation for force, F equals ma, torque equals I alpha. And if we take the spatial derivative of kinetic energy in a situation where all force applied contributes to kinetic energy, we also get torque. And then for angular momentum, well, if we take the angular analogy to mass, which is I, and multiply it by angular velocity, we get this equation, which looks very much like our momentum equation. And also another way we can get this equation is saying, well, what do we have to take the time derivative of to get torque? And again, this is the property we have to take the time derivative of. So this is why the concept of moment of inertia is so useful. Now, the question comes up then, okay, well, what if you don't have a point mass? What if you have some weird shape and it's rotating? Then how do you get the moment of inertia for that? Well, you just have to add up the moment of inertia for every single point on this mass, okay? You're going to have to take the mass of every point and the radius of every one of those points and add up the moment of inertia for all of that, okay? And what that turns into is an integral. So for example, let's say we have a rod, okay? And let's say its length is L, okay? And it's rotating around this point. And let's say its mass is capital M. What's going to be the moment of inertia for that entire rod? Well, consider a small section of that rod, okay? So small that its length is dx, okay? And, we're just going to assume this is like a one-dimensional rod, all right? So what exactly do we have to sum up here to get our moment of inertia, right? Well, we're going to have to take a sum from 0 to L of r squared times the mass. Well, what's the mass of that little section? Well, that mass is going to be the entire mass divided by the entire length, right? That's the linear density, multiplied by this dx. To be consistent, I'm going to call it dr. Okay? Multiplied by dr. Well, m and L are constant, so we can take that outside of the integration. So we just have the integral of r squared dr from 0 to L. And that is going to turn into L cubed over 3. So, simplifying that, we just have ml squared over 3. Okay? That is our moment of inertia for the entire rod. It's just an integral based on that same mr squared. Okay? Here's another example. Let's say we have a disk, okay? And that disk is rotating around some axis, right? And the radius of the disk is capital R, right? What will be the moment of inertia for this disk? Well, again, we have to add up the moment of inertia for every small slice of this disk. Okay, so we're going to have to take an integral over an area, right? So what's the area of that little slice? Okay, well, let's draw it out a little bit bigger here. Okay, we know that this part here, that length right there, that's dr. Okay, that's a small change in radius. And as for this curve here, well, that's like dl, but we know that L is equal to r theta. Okay, so this is actually going to be r d theta. Okay, so that little bit of area, okay, that little bit of area is r d theta dr. Let's set up that integral. Okay, so we have our r squared, and then what's the mass of that little area going to be, right? Well, the mass of that little area is the total mass of the disk divided by the total area of the disk, which is pi r squared. And we integrate over all of these little sections, right? So our integral, remember, right here, right? It's r d theta dr. Okay, that's the area of that little section. So let's do this integral. The m over pi r squared. Oh, by the way, it is a double integral where theta is integrated from 0 to 2 pi, right? Because we're going all the way around. And r is integrated from 0 to capital R, because that's the radius of the disk. So then we have our two integrals here. And we have a third r, right? So it's actually r cubed d theta dr. Okay, let's keep going. So m over pi r squared. Our integral with respect to theta is just going to turn into 2 pi. And our integral with respect to r is going to turn into r to the power of 4 divided by 4. And now we have a bunch of cancellations, right? So our pi's cancel out. Our 2 over 4 turns into a 2, and our r squared, which divides r4, just turns into r to the power of 2. So we have m r squared over 2. And that is the moment of inertia for a rotating disk. Okay? And for any other shape, the moment of inertia, it's just the integral of mr squared over an area or a volume or a length. I hope that helps, and until next time, enjoy.